Hello everyone, this is Nash. Today I would like to show you how to solve the rolling problems step by step. First, what we are dealing with is a rolling cylinder and it is now rolling down the inclined plane without sliding. So the first step is you're going to draw all the vectors of forces like the gravity. The first one, gravity, is my favorite because it's always pointing downwards. But however, your cylinder is now moving along this inclined plane, so the acceleration is now parallel to this plane. So the net force should be also parallel to this inclined plane. So I will not just simply draw the gravity pointing downwards. I would like to even divide it by two components. One is the x component, which is parallel to this inclined plane, and that is mg sine of theta. And the other one should be the mg cosine of theta, which is perpendicular to this inclined plane. And due to the mg cosine of theta, there's a force pushed back, and that is a normal force. And because you're accelerating along this plane, so the normal force should be equal to the opposite mg cosine of theta. That's no problem. And what is more, your cylinder is now rotating. If you set an observer standing right on the center of the cylinder, there should be a net torque. And what force caused the torque? Well, what force caused the torque? Because it is the torque that accelerates the rotation. And that force should be the friction. Since this is a rolling problem without sliding, your cylinder is now simply rolling down and it's not slipping. There's no movement between the surfaces of the cylinder and this inclined plane. So your friction should be static friction force instead of kinetic friction, static friction. So in order to solve these two problems, we got an SOP, a standard operating procedures. That is, we need to write down two equations. You will end up with two equations. And the first one is, I'm going to apply the Newton's second law. That is F equals ma. Newton says the net force acting on your object is equal to the mass times the acceleration. That's what Newton said. And the net force along this plane, along this inclined plane, is the mg sine of theta minus the opposite, because the static force is opposing its acceleration. The static force is pointing upwards. And mg sine of theta minus the friction force is equal to the mass and times its acceleration. You can say this, the acceleration of the center of mass. But at this stage, what we don't know is the friction, the size of the friction, and the value of the acceleration. And your math teacher tells you that there's no way to get these two variables done with simply one equation, so I need another equation. Simply by observing this cylinder, it does not only move along this inclined plane, however, it's also rotating even faster. So there should be a net torque acting on this cylinder. If you set an observer standing on the center of the mass, your gravity passes through the center of the mass, and your normal force passes through the center of mass. So both of them cause no torque. So the only one force that will cause torque, and that one should be the friction. It is the friction that causes the torque, and it is the torque that accelerates its rotation. So the next part is I would like to analyze this whole motion in rotational aspect. And similar to this F equals ma, we also have the net torque. The net torque, I use the symbol tau. The net torque acting on this cylinder is equal to the moment of inertia and times the angular acceleration. And the mass m corresponds to the moment of inertia, and the acceleration corresponds to the angular acceleration. If the mass tells you how hard to change a motion of an object, and the moment of inertia tells you that how hard to change something which is now rotating. Imagine something is now rotating. If it got a huge moment of inertia, then it will be difficult to stop it or to activate it. So this is the physics concept of mass and the moment of inertia. And for angular acceleration is just like the acceleration angularly. If something is now rotating, we get an omega. This is how fast you are rotating. And the change in angular velocity is angular acceleration. So this is tau, the net torque, equals I times alpha. So these two equations is similar to each other. And the net torque is caused by the static friction. So the F and times R that is the net torque, since the gravity and the net force passes through the center of mass. So the F is the only force, the static friction is the only force that causes the torque that accelerates its rotation. And it is equal to I times alpha. And this is one thing that you need to memorize. The moment of inertia for a cylinder is 1/2 mr squared and times the alpha. And the alpha, one more thing, this is a rolling problem without sliding. So there's basically no movement between the surfaces of your cylinder and this inclined plane. So for point P, imagine there's a point P on the edge of the cylinder. It has no velocity, but it does have with respect to the center of mass. If the center of mass is now moving with the velocity v, so the velocity for point P should be v with respect to the center of mass. Since it's simply rolling, there's no sliding, so the velocity for P is r times omega with respect to the center of mass. And of course, and the acceleration for the point P is also equal to the size of the acceleration of the center. And the tangential acceleration is also equal to r times the alpha. The A is the size, is the value for the acceleration of the center of mass. And for point P, it has no acceleration, but it does with respect to the center of mass. Okay, and the tangential acceleration is r times alpha. Is the acceleration of point P with respect to the center of mass. But your point P doesn't move at all. It's purely rolling. There's no sliding. So that is why the A, the tangential acceleration, is also equal to this acceleration of the center of mass. All right. So the A is equal to r times the alpha. I can plug in the r times alpha, and plug in this A equals r alpha back into this equation. All right. So I will simply separate them a little bit. That will be 1/2 mr and times r alpha. And r alpha is A, right? R alpha is A. I can even further cancel the radius r. So I now get the static friction is equal to 1/2 ma. So at the beginning, I don't know what is the friction. I don't know what is the acceleration, but now I know the F, the relationship between the friction force and the acceleration. So I can plug the F equals 1/2 ma back into the first equation. So now I got the mg psi of theta is equal to the friction plus ma, and the friction is 1/2 ma. So the total is 3/2 ma. So let's cancel the mass. So I now get the acceleration. The acceleration should be 2/3 g psi of theta. Done. So this is how we solve the rolling problem. I would like to know this acceleration. Even though the acceleration, you can also plug it back into the second equation, so you can get the static friction. So the static friction is also equal to 1/2 ma, 1/2 ma, and the A is this term. So you plug in this term back into the equation 2, I got F is equal to 1/3 mg psi of theta. So what we don't know at the beginning is the value, the size for the friction, static friction, and acceleration. Now I got these two variables done. If you know the acceleration, you can also further calculate how long should it take to roll down this inclined plane. If you are starting from v equals 0, and you are moving along this inclined plane for a finite distance, and the distance is, I give it a symbol as a capital S. So how long should it take to roll down this inclined plane? That would also be quite simple, because it's uniformly accelerated motion. So let's check if I have enough place to write it down. Let's just write it down. If I want to calculate how long should it take, I want to calculate the time t, because it's uniformly accelerated motion. So the displacement is also equal to v naught t and plus 1/2 at squared, since I assume that this cylinder rolls at the beginning has no velocity starting from v equals 0, so there's no v naught t. The first term could be cancelled. So the time t is equal to the square root of 2s divided by the acceleration. You can plug in a for a, and the a is 2/3 g sine of theta, and plug in back and replace the denominator so you can get the time for your cylinder to roll down this inclined plane. All right, so this is the SOP, the standard operating procedures for solving this rolling problem. And you know what? It doesn't have to be a cylinder. It can also be something that could roll, like a ring, like a disc, or like a sphere, like a hollow shell. Anything that can roll, you can solve it by using these two steps. The first step is find out the F equals ma, and the second step is find out the tau equals I times alpha. And you also need to memorize the moment of inertia for cylinder, for disk is 1/2 mr squared, and for a ring is mr squared, and for a sphere is 2/5, and for a hollow shell is 2/3 mr squared, if I'm correct. Okay, thanks for watching, and this is Nash.